What's up guys, it's me, Sir Ernest, and today we're going to answer example 1.11.2 of Fowles and Cassiday. The problem reads, on a horizontal turntable that is rotating at a constant angular speed, a bug is crawling outward on a radial line such that its distance from the center increases quadratically with time, given by r equals b t squared, and theta is equal to omega t, where b and omega are constants. The question is, the task is, find the acceleration of the bug. Okay, so for example, if this is your turntable, this is the center of your turntable, and this is your bug, so the bug moves radially outward. Okay, so that means if we're going to write the position function or position vector, it looks like this. So this is your position vector, and this position vector, okay, is defined by your polar coordinate system. Say if this is your x and y Cartesian coordinate system, this will be your theta. Okay, so you will notice that theta is positive, so the direction of the turntable is counterclockwise. Now, so we already know in polar coordinate system that the acceleration of the bug is given by a equals r double dot minus r theta squared dot, or theta dot squared r hat. So this is the radial component of the acceleration plus the angular component or the transverse component. That's r theta double dot plus 2r dot theta dot theta hat. Now we already know that r is equal to bt squared and theta is equal to omega t. So all we need to do is to get r double dot, r dot, theta dot, and theta double dot. So from here we can compute for theta double dot and theta dot. So we start with theta dot, r dot. R dot will now be equal to, so we just differentiate r with respect to time. That's the meaning of your dot notation here. So the answer is 2b t squared. Consequently, if we differentiate this again, this should be theta, t only, because we differentiate it already. So r double dot with just the derivative of this with respect to time, and this is 2b. Similarly, theta dot will be equal to omega, and theta double dot is equal to 0 because omega, we all know, is a constant. So from here we can now substitute these four parameters to our original equation for acceleration. Okay, so we know that theta double dot is 0, so this term will be 0, and then we just substitute the rest like this. So a, your acceleration, will now be equal to 2b minus r is b t squared, and then theta dot is omega, so this is omega squared r hat, then plus 2 times 2bt times omega theta hat. And then simplifying this, we now have 2b minus b omega squared t squared r hat plus 4b omega t theta hat. Or simply, you can factor out b. So this is 2 minus omega squared t squared r hat plus 4b omega t theta squared. So from here, we can now set that this will be the radial acceleration of your particle, of your bug, and this will be your transverse components of your acceleration. So the results show that you will notice that for sufficiently large t, okay, if this is large enough, the radial component of the acceleration becomes negative, while the transverse component, you will notice, varies linearly with time. Okay, so that means at the start, maybe if t is small enough, the acceleration of the bug in the radial direction is outward, but as time progresses, if the time is long enough, the acceleration becomes downward or towards the center of the turntable. Okay, so that's it. That's the solution to example 1.11.2 of Fowles and Cassiday 7th edition. Okay, so I hope you learned something today. Thank you for watching, and I'll see you guys in the next video. Bye-bye.